Hi, everyone. Thanks a lot for joining us for our fourth Urban AI conversation. I'm Hubert, and I'm the founder of Urban AI. So what is Urban AI? Urban AI is a think tank that federates a community of global pioneers in the emerging field of urban artificial intelligence. And together we propose ethical modes of governance and sustainable uses of Urban AI. But Urban AI is also a space for exchange, debate, and meeting, and this is why we organize Get Urban AI conversations. So today we have the great pleasure to have with us Shany and Ofir. So Shany, you're the director of the DD Lab for Disrupt Design Lab at the Technion, and you're also the co-founder of Shaga Architects, and you're also a contributor and advisor at Urban AI, and thanks for being with us today, Shany. Ofir, you're a product manager at Viv, and you're a researcher at DD Lab with Shany. And today, both of you are going to present us your latest research concerning patterns of livability. So you are going to tell us more about this topic. Very quickly, to give you some elements of context, we will have 20 minutes of presentations from Shany and Ofir, and then 20 minutes of Q&A session with all of you. So if you have some questions in mind, feel free to directly ask in the chat or keep it in mind for the Q&A session. Shany and Ofir, the floor is yours.
Great, thank you, Hubert. So I will quickly share my screen. Okay. Can you see my screen?
Yes. Okay.
So first of all, thank you, Hubert, for the invitation, and it's a pleasure also to be a contributor to Urban AI. So just to quickly introduce myself, so I am, as Hubert said, an assistant professor at Technion and the co-founder of Shaga Architects. And it's important to state both of these because this talk comes from the aspect of addressing practice. So how can we implement computational workflows that are coming from research into practical workflows that we as architects and planners encounter during the designing of projects. So both the lab and the office are dealing with these aspects, and the focus is to develop design-led technological tools towards real-world impact. So the lab has two streams. One is more data-driven, and one is more digital materiality. And today we will focus really on computational workflows that are addressing planning bottlenecks. And I want to start with this basic iconography, which of course most of you don't understand the language, but numbers are universal, so that's always good. And what this shows is iconography about Israel planning processes, which states that an average of 27 different disciplines participate in the planning process, and the average time duration from inception to the population of neighborhoods is 15 years. 8 out of them are design development phases. So here we understand that computational workflows that have to address planning require multi-criteria assessment to be able to understand the trade-offs between the different disciplines that are coming into the design process, but also have to be interactive throughout the duration of the planning process. So today the office, Shaga Architects, is involved in many large-scale planning projects in Israel. And through that, what we do is we develop computational workflows that incorporate design decision-making within instrumental bottlenecks in what we detect as municipal challenges. I will go through this very quickly because just to enable enough time for Ofir to present his work. But in a way, what we do is we develop generative models into a design search space, and I will show the examples in a second. And we develop classification criteria in order to be able to make informed selections of design scenarios to be taken forward based on quantifiable indicators that can be discussed, assessed, and evaluated. So the first thing is the generative design model, which is built on a selected number of indicators that then can be formulated in different types of inquiry analysis in relation to what the inquiry question is. From this, we move to the search space. So the search space is where we actually ask questions about the relationship between the different indicators that come into each plan. We can look at them per indicator, so to look at each aspect from an expert contribution, or we can start to understand how to relate different indicators to each other, as you see on the top left, where we relate diversity, microclimate, and density on one building block, so the same building block that you see on the right. And at the bottom, what you see is another resolution of inspection, which is a pass-fail. So in related to specific indicators, how do we assess the basic pass-fail? So not a quality check, but a pass-fail check. What is important that as planners, although that sometimes when we encounter the municipal engineer, he only wants to know the pass-fail, what we as designers need to be able to understand is also the actual quality of the design and to go back from the pass-fail to the actual performance, for example, here of microclimate of a specific neighborhood. And the last aspect I will show just before we move forward is the understanding of classification. So on the one hand, we can look at indicators that go into every urban plan. For example, microclimate, diversity, and density, as I was discussing before, and many more. But the idea of the classification and the way that we use the clustering algorithms is actually not to look at the potential design in relation to specific indicators, but to look at them in terms of spatial qualities and understand the impact of the indicators on each and every scenario. So this was just to outline a very specific framework that we work with on municipal projects. And maybe to underline the basic question that I ask researchers at the lab, which is, how do we create meaningful knowledge for design support towards sustainable and livable implementations? So in a way, this was the question that I put forward to Ofir, and then Ofir selected a topic to address these questions. So I'm now going to stop sharing and I will give the stage to Ofir, and he will go into his thesis project. I'm trying to. Hubert, are you able to kick me out? Because somehow I'm not able to.
Right, I might be able to do that.
Ah, here, I did it. Okay.
All right. So, see my screen?
Yes.
Perfect. All right. So, yeah, so as Hubert and Shany presented, my name is Ofir Zak. I'm a practicing architect, also an urban designer. I've been practicing for quite a long time, both construction project and urban design projects across Israel. And lately I moved to a startup, Viv, look it up. In parallel, I'm a researcher in Shany's lab, and today I'm very happy that I have the opportunity to present you with a small part of what we do there. So, what began this journey, this research, was really the last 2 years, where globally we're trying to cope with the new risk of the COVID-19, same in Israel, obviously. And some of the actions that were taken by the governments were restrictions on mobility. At times it was 1,000 meters away from home, sometimes 500, and sometimes we were limited to 100 meters from home. And this was, for many people, quite a hard experience, but to me it made me very curious. I realized that the neighborhood I currently live in has a much bigger variety and much bigger quantity of services of all kinds than the neighborhoods I lived in before. And then I simply opened, as you can see on the right side, the city's GIS. I looked at services, and unsurprisingly, I figured out that that in a more central places or a more hype places, you've got many more services than in others. Then I took a piece of paper, which you see on the bottom left, and I started sketching houses and services and measuring conceptually how these can be like measured in terms of region or neighborhood. And I figured out something that was kind of interesting to me at the time, that depending on the bin that you choose or the boundary that you choose, you get different insights or different results. And as I said, I became pretty curious about it, and I decided to go ahead and develop that into a proper research. So one of the main topics that I had to deal with was livability, a term that I did not know by then, but when I started to study into it, I found an overused term, or a term that have become in the last few years a buzzword, to a place where it kind of lost its meaning. But out of the really enormous amount of definitions out there, I found this definition that you can see on the center here, that I went with, and this is the extent to which a city can satisfy the physical and psychological needs and demands of its residents. That's SPATIAL, very recent actually. And as an architect, and because I had quite a lot of experience in urban design and in the urban making, I really wanted to see what is our impact as architects, as planners, on the aspect of livability. So I focused on built form indicators. I looked at different rating systems, trying to because one of my inspirations was to try and really quantify livability. So I looked at rating systems, and apparently I found a sustainability rating system, or SRS, as a good source for livability measurement, because even though they are defined as sustainability, which is by nature a wider or a bit wider topic than livability, it deals with where does materials come from and how does the city affect the nature and so on. It is still used both for PRs and for other reasons for actual livability assessment, and there's actually quite a lot of literature discussing specifically the usage of those systems for livability measurement. So I looked at those rating systems, and I figured out that there are three main drawbacks to all of them. The first one is that they rely or partially rely on experts' opinion, what makes it subjective rather than objective assessment. Then the second was that it takes a lot of time to get a rating from these systems, what makes it not so useful in terms of being integrated into the design process, where time schedule is short and so on. And then last, as in my hand sketch, they all take in account specific arbitrary or administrative boundaries, and they measure different aspects within those boundaries. And by doing so, they are exposed to a type of bias, a bias that is known as the MAUP, or the modifiable areal unit problem, which OpenShow wrote about in the mid-80s. This bias is basically caused by choosing bins that are not appropriate for a task. And as we can see, quite contemporary example on the right side, which are elections, US elections, divided once aggregated once by state and then by county, you actually get a very different insights. So there we go back. So we have these three drawbacks, and that led me to define myself as an objective to develop a computational framework for spatial quantitative generation of livability focused regions. I wanted this framework to be scalable, So I can use it on different scales everywhere I want in all over the world. I want it to be flexible, so I can control which parameters, which indicators will be taken into account quick. So it had to be automated and computational by nature. It was important for me that it would address such biases as the MAUP, and I really wanted to make it to base it on open data. The reason is that, again, based on my experience and based on a lot of literature, different municipalities provide with different types and different levels of detailing of urban data, and that is quite a challenge to be based on municipal data and still have it scalable, flexible, and so on. So I built this talk more like a discussion. I want to show a bit of what's going on under the hood, more than take you through the workflow and come up with one conclusion. I'll start by taking you through the workflow, and then I'll focus one by one on areas that rose questions and challenges that we discussed within ourselves. So we begin by extracting data or downloading data from OSM. I will explain OpenStreetMaps. It's a platform that allows open data mapping. And then in parallel, we build a street network and define basic spatial units, or basically the units that we are going to use in order to aggregate data to, which are very small in order to allow us to avoid the MAUP bias. And in parallel to that, we choose what indicators to look at, and we calculate them per each of the BSUs. We then weight them and put everything into a clustering algorithm, an algorithm that allows us to collect together groups of basic spatial units, groups of observations that feature higher similarity within a region or within a cluster than outside a cluster. If this sounds a bit complicated, I will explain everything in the next slides. So I'll show you the Tel Aviv. Basically, the case study I'm looking at is based in Tel Aviv, my hometown. Tel Aviv is in Israel, of course. Is divided to 9 administrative regions and then to 47 neighborhoods. And we start with the open data. So maybe it may sound like an ideal or something that it was one very important aspect for me, but then it brings with it quite a lot of challenges. So to understand the type of data that we download from the OpenStreetMaps is mainly one of those 3 types: streets, buildings, or points of interest. And while street and buildings are pure geometries and are kind of reliable and easy to work with, points of interest are an aspect that is mapped by the public, for the public, and the public as publics are not always very much educated. They basically, although there are some guidelines to how you map data on OpenStreetMaps, and this is being improved all the time, there's a lot of data, and this data is not always well classified. So streets were pretty straightforward, and we were able to extract the intersections from it. I always start with streets and intersections because maybe that is not so obvious, but I always start with street and intersections because we're dealing with livability. We're dealing with how people are using the city, and the way we see it is that any movement, any usage of the space is based on how you get to and from these places, and therefore this is my first move. But then we're dealing with points of interest, and again, just to explain how this works in OSM, every entity, every object in OSM can be pulled, can be downloaded, but you need to know what is how to address it. And the addresses in OSM are built like key and value. So keys could be amenity, shop, highway, and so on. Value is a restaurant, bus stop, and so on. But then if you look down the screen, you'll see that there are almost 2,000 most common keys and almost 10,000 most common objects, what makes it very, very hard to navigate in. Part of the reasoning is that, again, because not all users are following exactly the guidelines, you see on the left side of the screen how many different versions of the key amenity are there. So we developed a method in which we use the recommended form of every key, and we use a website called TagInfo that provide the statistics. So we get the most common tags associated with the key, and then manually, at least for now, we filter and classify the tags per category and per the requirements of the chosen sustainability rating system. So we downloaded the bus station, the public buildings, and all types of different data. So basically, you get quite a lot of data relating to your city. Next, building the basic spatial units. Traditionally, cities are represented in one of two ways, either tabular data or as a network. Each of them has its own advantages and disadvantages. We actually wanted to take the best of both, and therefore we went with a solution of tiling the space into a Voronoi-based basic spatial unit. I will show that in the next slides. And to define network-based spatial weights. Spatial weights are the way that different tiles in space relate to each other. So traditionally, in urban analysis, there was a grid put on top of the map, an equal grid of say 100 by 100 meters or 200 by 200, and all kinds of data were measured within those cells. Each cell would get like a mark, and then if you would like to model relations between the cells, there were two typical ways of doing so: either rook based, so that's basically all of the perpendicular neighbors, or a queen approach, which would add also these diagonals, and then all of these would be called neighbors of the central cell. More recently, research have moved to hexagonal-based grids, which always uses the queen type. It's a bit better. It's a bit better in terms of statistics, but the differences are not very big. What can be seen in both approaches, that none of them relates to the network. And therefore, our approach was based on Voronoi cells. Voronoi diagrams are taking a set of points, in our case, the intersections, and they tile the space in a way that each cell represent the area that is in biggest approximation to its core node, to the intersection. So these are the spatial units that we used in, and we got a tiling of Tel Aviv based on Voronoi cells. Into these bins, we will aggregate all types of data. In parallel to that, Hubert, can you just tell me how are we with time?
Yes, it's okay. You still have like 10 minutes. Perfect.
Sounds good. So in parallel to that, we needed to define which indicators will be taken in account. And to do that, I chose the neighborhood 360, which is the Israeli local sustainability rating system, because in the case study we're dealing with Tel Aviv. As a matter of fact, all of the systems are very, very much alike. Like they take a lot of inspiration from one another. So but that was a choice. And we filtered out of these 47 possible indicators in neighborhood 360, 8 indicators that represent the effect of urban form on livability. By the way, these 8 indicators, they make up a bigger weight in terms of points you can get from than their relative number. Each of those indicators was analyzed. That's Hebrew, but each of them, according to the instructions, each of the indicators was analyzed in order to extract which are the parameters that we need to be able to download from OpenStreetMaps or whatever database we rely on. And then we filtered it once again to 4 indicators that are not only represent the effect of built form, but also are available for measurement only relying on open data. Each of those indicators was translated into a workflow or a computational workflow that allows us to automate the process. And so we've measured each of those indicators, and there are 4 indicators, but actually there are many more sub indicators, as you can see, like different categories and so on within each of the indicators. So all of these measures were made on top of the basic spatial units, and then we go on to the clustering. So having so many mappings is something that is great. But if one of you have ever tried to plan to make a urban design or city planning, you understand that this data is very hard to manipulate, to use or to understand without the help of computational tools. And the algorithm that we chose of clustering is an algorithm it's an algorithm that is not very popular, let's say. The reasoning is that typically in many of the researchers that you see, they rely on k-means algorithm. It's a very popular algorithm. It does not, though, take in account spatial constraints, or neighboring cells are not taken in account when doing the clustering. We wanted to have regions, and therefore we went for agglomerative clustering, and specifically to spatially constrained clustering, that allowed us to group together cells that are both similar in terms of the parameters tested, but also in adjacent in terms of space. And we started to cluster Tel Aviv based on our parameters in different numbers of clusters. This is a whole different discussion on how many clusters should be used, and one of the limitations, let's say, we have with this clustering algorithms, that they ask us to provide them what is the right number of clusters that we want to get. And so, but I think that with every k number, k is the number of clusters, which every k number we can see different aspects of what insights does this clustering gives us. So with k2 of 2 clusters only, you immediately see how the algorithm recognizes the heart of the city, the center of the city. And when we go up to 5, 7, and 9 clusters, so that we can compare with the number of quarters we currently have in Tel Aviv, we can start seeing patterns of how the south is very well defined. No matter how many clusters you go with, south is very well defined in terms of this of its livability performance. And when you put our clustering on top of the current quarters mapping of Tel Aviv, so questions start to rise, and I'm not going to provide you answers, but I would just say that interesting things that we can see is, for example, if you look at quarter number 7 is Jaffa. It's the south of Tel Aviv, and when you cross-check it with a socioeconomic or with major religion and so on, you start seeing that the original partitioning of defining cluster 7 is much less accurate than a livability-based clustering that we see here. Now, just one notion on that. The clusters here are not defined by level. Okay, I cannot say that cluster number, that the purple cluster in the center is more livable or less livable than the green one, but by type. Since we have an n-dimensional, or let's say the number of parameters that we check is n. So an n-dimensional space, and the different basic spatial units or the observation are placed, like you see here in the bottom left, in this n-dimensional space, then it just says that it's relatively much more similar to its surroundings than to other places. And then this, as I started to explain now, we can keep on and studying the differences between the resulted zones and the administrative zones and so on. I will just show you maybe one example, because I think it's about time. I will just show you one example. As you see here, this bit, it's from an aerial, but this bit is considered administratively as part of the lower neighborhood bound by these lines. But if you look at its appearance, it's actually much more like the one on top. And then, oh, sorry. Okay, and then the algorithm actually derives the same conclusions, saying that this bit here, the purple bit, is actually much more like the top than those areas next to it. And again, I was hoping less to provide you with answers and more to start a discussion. So that's it. Thanks, Hubert.
Thank you very much, Ofir and Shany, for this presentation. Very insightful presentation. I'm from France, where we have a lot of regulations, a lot of laws, so I really see how insightful could be your work. Do we have maybe some questions? So you can use a chat if you are shy, or you can directly raise your hand and discuss all these topics with, yeah, go on, please.
Thank you, Hubert. Shalom, Ofir and Shany. Nice to meet you. Quick question, well, actually to each one of you. So I'll start with Shany. I think your first slide was incredibly interesting and frightening at the same time. The duration of planning processes are just immense, both in Israel, but I guess it's spreading across the entire world. I'm wondering how well your algorithms, the generative algorithms that are becoming very, very popular nowadays, how well are they predicting changes over the course of that duration? That is to say that the algorithm can produce any number of potential designs at this very moment and do some kind of nowcasting, but how well are they predictive in terms of the changes occurring between now and the beginning of the construction on the site?
So I'll answer that. Thank you, Ariel, and nice to meet you as well. So yes, I always put this iconography because in a way it's obvious, we should know this, but it's shocking to see. And in terms of the way that we develop the algorithms, at the moment, I have to say that the predictive qualities are not so good. I'll put that first before I now start to explain why they're still effective. They're not good because it really relates to the design culture, and here I'm talking only about Israel. So in order to predict, you need to make assumptions, and it's very difficult at the moment with also political, legislative, and standards that are being put in front of planners to be able to make assumptions that actually hold water. But what they do enable is they create a live model. So in a way, this is not a digital twin, in no way, because this is supposed to support design decisions, okay? It's not but because the design process is so prolonged, so we're not talking now about physical form that is built, but we're talking about a physical a digital entity that is supposed to simulate interactions through time, then what it does, it enables us to update, optimize, and make, I would say, short-term assumptions that actually become very informative within municipal processes. So I think the question is, I mean, it would be very interesting to take the same workflow and try to maybe use it in a place where actually some of the legislative aspects are much more solid, if I can be polite in that sense.
Great, thank you. Hubert, can I have a quick follow-up with Ofir? Thanks. So thank you, Ofir, as well for your talk. Just a very sort of technical question. I'm wondering if through your clustering analysis, did you find any specific variables that are more independent than others, sort of instrumental variables in the analysis? That's to say, which were the ones that were triggering, kind of aiming towards finding the clusters more than others, whether, you know, agglomeration of restaurants versus socioeconomic situation?
Yeah, it's a good question. This analysis is not complete, so it's only a beginning of it. But at least for the case of Tel Aviv, it seems like and again, maybe knowing Tel Aviv, maybe it's not a surprise. But yes, leisure amenities are, let's say, by themselves are providing the best indicator for the overall livability analysis. It's the most prominent indicator, but I'm not sure at the moment if this will be the case for every place. I think that part of the problem, let's say, that by using open data, and maybe it was a good reason to choose Tel Aviv, is that it is very much affected by what is mapped and what is not mapped. It's right for any type of data, but let's say you have you don't have much control of it when you're using open data. And then Tel Aviv is a good example because it's like medium level mapped. If you look at places like New York or in London, you really get a very intense mapping going on, and that might change the results.
Great, thank you both.
Hi, can I ask a question?
Yeah, sure.
Hi, hello. So I have a question for Ofir. Hi, my name is Do. I'm from Bezalel Academy of Arts and Design. And I saw that you decided to use the Voronoi pattern And the first thing I asked myself was why not using the block and parcel data that is available for Tel Aviv. And then I realized that you want to use the nodes in a graphical algorithm to define a parameter you call urban fabric. Now, can you expand on what are the principles which define the fitness of this parameter? I saw you were talking shortly about the length of the street and the distance between streets.
Yeah, I think if I understand right, your questions have two aspects. One is the choice of a Voronoi diagram over a more traditional partitioning of the space. By the way, it's worth mentioning the work of Martin Fleischmann, that maybe some of you are aware to, which developed MAUP. It's a Python package that one of its features is really partitioning of the space based on buildings and its near surroundings. So as I said, each of the approaches has its own advantages, but one thing that even looking forward into the next research and so on, I wanted to give more weight to the network structure of the city. And to do that, I was not able to use neither plots or by the way, plots touching again in your question, plots might be good, but they do not take in account, let's say, the streets and areas that are not plotted, let's say, in a way. That is why MAUP, for instance, is dividing the entire space based on buildings, and it's very, very similar to plots, but not exactly plots. There was a quote in the presentation by Einstein that everything should be made as simple as possible, but not simpler, which is a quote I like a lot. And looking forward to what can be done with this approach, I think that representation as a network also opens up quite a lot, or an attributed network, which is not as often used. It opens up a lot of opportunities for analysis that is based on network analysis methods like connectivity and so on, and that derived my decision.
Thank you. Actually, my question was more about the
right. Sorry. You're right about the parameters. So
yeah, especially the urban fabric parameter, which in my mind is the most interesting one.
Correct. The urban fabric was not a parameter that I used. It was one of the 8 parameters that was that I first chose, and then it was omitted in the second phase because of the lacking of data in OSM. It is indeed a very interesting parameter. I'm not sure it's the right timing to elaborate on that, but it is a very interesting parameter, and if you can, we can discuss it later.
Thank you very much.
I also have a question, actually, Ofir and Shany. It's a kind of a very naive question, but so when we have this new typology, this new map, which are, as you've just shown in, much more accurate, how can we use it to have like more livable cities?
I think that part of the answer is in your question. The mapping, the currently available mapping, let's say if we look at traditional administrative regions and so on, the problem with this is that they are fixed. They're fixed, and you use the same type of partitioning, the same type of beans for every question you ask. And part of the solution for the MAUP problem is that you create your own bins for the right question, for every question you want to ask. So that is why I keep saying that as far as the selected parameters and for livability analysis, this mapping gives you a more accurate picture of how the city functions. So what can be done with that? Once you analyze the regions, if you're taking, for example, a region and you analyze its performance on the different indicators, you can provide stakeholders with a clear picture of what should be improved and where. I hope that answers your question.
Yeah, yes. I just want to add to that one more thing. I mean, today, a lot of municipal processes are, especially in Israel and especially in Tel Aviv, and part of the processes that we are developing is also new policy documents for planners. And the idea is that if we can start to define policy documents that are interactive rather than reports, as they are today, that we understand the consequences of the design decisions that we make, as both from planners and as the designer sitting in his office. I mean, suddenly we start to synthesize knowledge into our design decisions. So I think it goes both ways. I mean, there is one is the knowledge to introduce, let's say, so it's not what the answer is, it's what's the question. I think that's what Ofir was trying to say. But the other thing is, how can we use the questions to inform our design decisions? And these are the two aspects that we're trying to move forward with.
And I had another question that I asked, waiting for another one, is do you see some oppositions that I don't know you could face with your tool? Maybe political opposition, because if I take the example of Paris, we have some 20 districts. This is, as you stated, in a way not the perfect way to represent Paris, but for each district we have a mayor. And each mayor wants to stay a mayor. So that's what I had in mind.
I'll take it.
You start, yeah.
Okay. No, I think first, let's say learning from practice, finding opposition is the easiest thing. Anything you will ever propose, there will be opposition. But then I think if I'm adopting your example to a local discussion, let's say in Israel, Tel Aviv is surrounded by many smaller cities. Five cities, I think, are surrounding Tel Aviv, and it's actually touching Tel Aviv. And each of those has its own mayor, of course, and it's a different administrative authority. I'm sure that such analysis could cause contradiction to their could be in contradiction with their interests, their political interests. But I think that the smart way it would be to use that to raise questions, less than providing answers.
Yeah, I mean, I will add that we see this more as a kind of a bottom-up operation rather than a top-down, although we are looking from the other lens. So both with understanding that we need to generate the information coming from open access data, but also to bring knowledge from the designer to the municipality and not just the other way around. So for me as a designer to be able to inform a legislative representative that he should be asking a different question. And I mean, we're not in the profession of being all right with everybody. I don't know how to say that. I mean, we're in the profession of trying to make the living fabric, or as we're trying to generate livable neighborhoods. So we see that as our job. And of course, provocation comes in every design process that we ever do. And whoever has ever planned a big planning project knows that provocations are part of the deal. So actually, I find that as something that we're waiting for these provocations to come to see how we can address them. But what we are relying on is that we're coming with quantitative, analyzed data that can support our arguments. And I think that's maybe what is sometimes lacking.
We have, maybe it will be the last question in the chat. So Ofir, it's for you. So the question says, I'm not familiar with how the spatially constrained clustering algorithm approach the weights of given parameters. Do they require some extra normalization or manual weight turning? I'm wondering whether this algorithm treats the parameters equally, or does it weight them in some sensible way? Okay,
that's a very technical question. I will try to explain briefly. Attributed networks can basically be imagined as a set of two tables. One table would be in a dimension of, let's say you have n a number of intersections or basic spatial units, so n by n, and in this table, every cell would say 0 if they are not neighbors, or a float, a number, if they are neighbors. And if we go for a weighted approach, then this number will represent the strength of the connection. So in my case, I weighted it as the length of a street segment between the nodes. The second table is an attribute table that represent which attributes are associated with each of the nodes. And then it's n number of nodes by m number of attributes table, and on each cell there is a float representing the strength of a specific attribute in the specific node. The algorithm, or the spatially constrained algorithm, is taking the second table, as every clustering algorithm, taking the attribute table and represent it as a m-dimensional space. So if m is the number of attributes, there are m dimensions, and each get a node. But then on top of that, it basically multiplies the vector length in the strength of the spatial weights when it tries to decide if to join two observation or not into the same cluster. So if two observations are not adjacent, they will not be joined. They will not be joined because it multiplies by 0. I actually, rather than explaining it by verbally, I highly recommend on going back to the origins and looking at regionalization algorithms. You can type in Google AZP or agglomerative clustering. sklearn package in Python has a very good documentation regarding that this algorithm. Or even going back to OpenShow, which explains it perfectly in an early article from 77, if I recall.
Thank you very much, Shany and Ofir, for this very inspiring presentation. Thanks to all of you for attending this session. It will be available on our YouTube channel in the coming days. And our next Urban AI conversation will be in 2 weeks, and it will be in partnership with All Things Urban. It will be about how to get a job in Urban AI. So 5 inspiring experts from Urban AI community will come and explain you their job, their studies, etc., etc. Thanks, everyone, and take care.